All right, so we're back with set number 10. Set number 10 is two problems and then an additional problem that a professor gave to us on our handout. Let's do the additional question first. So I've kind of already got this, this worked out here. All right, so using the equilibrium principle like we've done in chapter 4, and knowing that our system is not moving, so things aren't sliding this way or sliding down. We have kind of a still motion. We know that the forces in the x direction all equal 0, and the forces in the y direction all equal 0. And so we can set up our problem and split them into x and y components, find out what we need. All right, so let's start with x because I don't know, because I always do if I can. So we know sum of fx's is going to be 0. We can take a look at this little diagram that I've drawn that professor drew for us on our handout. We can see that the force in the x direction is going to be T1 sine 40, and the force of the, let's say the second triangle in the x direction is going to equal that, because if we set that to 0, there's only two forces, they're going to equal each other. So slap in some values here, and what we end up with is f of x2 is 22 newtons. So given that, now we can solve for both of the y components of the force within the triangles. We couldn't do that before because we only had one angle. So again, we know this. Using that, we are going to find f of y. So we have T2 squared, which is going to be our A, equals f of x2 squared plus f of y squared. Plug in our values, and we get f of y, or the y component of the force for the tension in the second string, is 33 newtons. So now we can put all of those together in sum of the forces in the y direction equals 0. We've got the two tensions in the y, and then we also have our mass that gravity is pulling down, that's pulling in the opposite direction. So we'll set that to negative, plug in our values, and we end up with 6 kilograms. All right, so moving along to problems from the book. Let me pull up the book. All right, so the first problem that we've got is chapter 7, gravitation only. Problem 37. Objects with masses of 200 kilograms and 500 kilograms are separated by 0.400 meters. A, find the net gravitational force exerted by these objects on a 50.0 kilogram object placed midway between them. All right, so let's start by drawing a little picture. Whenever we're doing gravity stuff, I always make our objects circles. Left with enough time, gravity is going to pull an object into a circle or a sphere. So that's when you see gravity problems, you're always going to see little circles that I've drawn. So let's go ahead, draw some circles. We've got M1 over here and M2. If we were to put something right here, we'll call this M3. We want to know the net gravitational force exerted by these objects on the 50 on mass 3. All right, so we know M1 is 500. M2 is 200. M3 is 50. We know this principle. The gravitational force is G, which is the gravitational constant. Large mass, smaller mass divided by r squared, or the distance between them. All right, so let's start with the big one. We're going to assume that that's going to be the larger force that's felt here. So we're going to do f of g equals g, which is a gravitational constant, which is 6.674 times 10 to the negative 11. Oh, we do. Meters cubed, kilogram, second squared. All right, so we'll leave g in until the end, until we get out our calculator. So big mass is 500, little mass is 50, distance between them. So now we're given the full distance between 1 and 2 as 0.400 meters. Right in the center, we're going to say, if we call this our origin, this then is going to be 2, and this is going to be 2. So our distance between them is going to be 2 squared. And if we get our calculator and we put in all of our values, including g, we end up with 6.25 times 10 to the 5 g. Then if we stick g in, oh, you know what? I actually waited until the end to put g in, so we will not use g yet. All right, so now let's find the force between M3 and M2. Fg, 1, 2. We've got g again. Our big mass is going to be 200 now. Our little mass is again 50. Distance is going to be the same. And we're going to get 2.5 times 10 to the 5 g. All right, so now let's look at our picture and let's figure out how we find the net force. All right, so we've got FG1 is here. FG2 is here. The net force is going to be the addition of those two. Because they're pointing in opposite directions, they're going to not completely cancel each other out because the masses aren't the same, but they're going to add together. One of them is going to add together in a negative way, and there really isn't a negative gravity. When we use negatives, what we're saying really is that is in the negative x direction, or negative y, or negative z, however your problem is set up. So we can just call our origin right here. We can say that this is positive x and this is negative x. So we're going to add FG1 plus FG2 to get our net force. So our 6.25 times 10 to the 5g is then going to be negative 6.5 times 10 to the 5g. Net force 10 to the 5g plus 2.5 times 10 to the 5g. Now we're going to use our calculator. Now we're going to plug in the 6.674, whatever it is. And we are going to end up with negative 2.50 times 10 to the negative 5 newtons. That is our answer for A. Did I be able to say it? I did not. All right. B asks, what was my textbook? B asks, at what position other than infinitely remote ones? Because we know that if we send something infinitely far away, the force of gravity goes to 0. That's kind of a cheater answer. So they wrote that into the question. Don't even try that. We're not buying it. At what position can the 50.0 kilogram object be placed as to experience a net force of 0? So if we know that our M1 is bigger, in order to get a net force of 0, we're going to have to decrease R between M2 and M3 to increase the force, because we're not making the mass bigger. We need to find where that equilibrium is. So equilibrium, we know, is forces, we set forces equal to 0 in this case. If we do that, we're going to have FG1 plus FG2 equals 0, or we're going to have FG1 equals FG2. All right, so again, we have the G times big M times little m over R squared. We're going to have that for both side 1 and side 2. So we'll do G. We'll label these as M1, M2, R squared equals G. That's not M2, that's M3, sorry. M2, M3, R2. These cancel. These cancel. So you can see when we're balancing gravitational forces, the mass of the object doesn't matter. It's kind of an important principle that I don't know that you get into in this class. However, something kind of funny to think about, that the size of that object doesn't matter. Anyway, okay. I'm getting into physics speak, who cares, right? All right, so if we are to set these equal to each other, we get M1 R2 squared equals M2 R1 squared. We know M1, we know M2. If we plug in those values, we get 4 R1 squared equals 5/2 of R2 squared, or the distance between masses 1 and masses 3 is equal to the square root of 5/2 times R2. We're just going to leave that as the square root of 5/2 because we're going to get a point, blah, 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 and square root of 5/2 is exact. So now we're going to take that and we're going to shove that into another equation to solve. But what other equation do we have to solve? So if we go back and we look at the original diagram that we're given, our masses aren't going to change. The other thing that is not going to change is going to be the total distance between M1 and M2, and that's 0.4. So we can write an equation that says R1 plus R2 equals 0.40. So now the distance between M1 and M3 is going to change. The distance between M3 and M2 is going to change, but the full distance is not going to change. So we can use this equation. We can shove this into here and we get square root of 5/2 R2 plus R2 equals 0.4. And then if we add everything, divide everything, we end up with 2.58 R2 equals 0.400. Do the math, you get 1.55 M. Then we can take that and we can shove that back into our other equation. and we get 0.245 m. If we add those together, we're going to get 0.4. And as you notice, what we would expect to see, we expect that M3 is going to be much closer, or R2 is going to be much smaller than R1. That's what we see. We got the right answer. Woohoo! Moving right along. Not going to post another hour video for you guys. All right, 40. You're trucking here. All right, two objects attract each other with a gravitational force, because all objects attract each other with mass, of magnitude 0.00 times 10 to the negative 8 newtons. So they're barely attracting each other when separated by 20 centimeters. If the total mass of the objects is 5 kilograms, what is the mass of each object? Okay, so let's again draw a diagram. Here, here. We are given that this is 20 centimeters. We are given M1 is, no, we're not given M1. We're given the net force between the two equals tiny little number times 10 to the negative 8n. We are given that the addition of M1 plus M2 equals 50. Oh, sorry, 5. It's fun to think that these two tiny little objects actually feel a gravitational potential for each other. If we were not close to the center of the earth, these tiny little objects could rotate around each other. Gravity is really cool. All right. But unfortunately here, close to the center of the earth, our gravity is too high for these things to happen unless we're in a lab making special circumstances. Okay, so we know this, so let's solve for M1 just because it's, easier. Again, I'm inherently lazy. We know this. And we are going to solve for M2 because we solved for M1 in here. And so we're going to shove this in here. We're going to have two M2s. Usually I try to shove everything to one side. This one gets a little more complicated because we're actually going to have to use the quadratic to solve it. So we're going to leave it as it is. We're going to do all our math to find out what our A, B, and C is for the quadratic. And then we're going to shove everything as we need to. All right, so FG equals G times 5.00 minus M2 times M2 all over the distance between them. All right, so if we do the math here, we get 1.00 times 10 to the negative 8n equals G M2 5 minus G M2 squared all over R squared. That's not R2, that's R squared, sorry. All right, so, oops. So we're going to shove the R over here, and that's to 20 squared. G is 6.674 times 10 to the negative 11. Going to kind of skip, straighten out our units here. Minus 6.674 times 10 to the negative 11 times M2 squared. All right, so let's rearrange this so that we have an equation that looks like this. And then let's figure out what our A is, what our B is, what our C is, and then shove it into the answer that we know, which is the negative B plus minus square root of B squared minus 4AC all over 2A. There are other ways to solve a quadratic. when in doubt, just use that. And I think they specifically want you to use that because I know Professor put that in his on his notes last week, I believe. So we know b squared minus 4ac 2a. Let's figure out what's a, what's b, what's c. All right, so we got this. We know that m2 is going to be our x. So we've got negative 6.674. You know what? It's easier just to get rid of this, and that's what I did in my original answer. So let's divide everything by g and then get g over here. That way we just have a -1 for m2, or if we rearrange everything, we can have just a 1, which makes our life easier. So let's do that. Let's divide everything by g, and then we have, and then we'll shove this over there to get a positive. So then we have m2 squared minus, minus m2 times 5 plus 1 times 10 to the -8 times 20 squared all over g equals 0. All right, so we've got, this is c because there's no m's. This is b because there's 1 m, and this is a. When in doubt, trying to get rid of things if you can is always best. We've gotten rid of a here by shoving stuff over to one side. All right, so if we were gonna throw our values in, we're gonna have x equals positive 500 because our b is a negative, plus or minus square root of 5 squared minus 4 times this thing, let's call that c, all over 2 times 1. Okay, so you will notice here, if you make that plus or minus a plus, you're going to get something that looks like 1.02, which gives you oh, sorry, that's not. You end up with 5 plus or minus 1.02 times 2. If you choose plus, you're going to end up with something that looks like this. So if you do minus, you're going to end up with something that looks like this. So how can it be, how can it have two values? It can have two values because gravity doesn't care what direction it's in. And so you're either going to have M1 being here or M2 being here. So M1 and M2 together have to equal 5. So M1 can either be 3 or it can be 2 because the system doesn't care which mass is where. So you end up with M2 equals 3 or 2. And we know from reading the question that they equal 5 kilograms. So if M2 is 3, that means that M1 is 2. And if M2 is 2, that means that M1 is 3. And that is our answer. All right. Thank you so much for listening. I will see you again next week.